The field of AI has had a long, generally unrequited affection for game theory. Thus, developing a superior AI to play the game Clobber, which was developed by game theorists, seemed a natural fit for an AI course. Our research was only able to uncover a single paper from 2011 with Clobber AI algorithms, and that paper failed to provide code. Without an available opponent, our focus shifted from creating a superior AI to creating an AI which could play the game at all. At minimum, we expected to be able to consistently defeat a random AI. We believed we had time to craft an AI superior to a standard Monte Carlo tree search, a premier AI game technique. It's been used by groundbreaking programs such as AlphaGo. As there was not publicly available code for MCTS for Clobber, one of our tasks was to write that program ourselves. We named our program theClobbit, and I'll describe its internal workings in a little more detail in a moment. First, its performance. To calibrate, we started with random versus random, which gave us just about a 50-50 split, with a slight advantage to the first player. This is interesting and ended up holding true throughout the trials. As we tried the individual elements against themselves, you can see that the first player advantage grows more and more stark. Finally, the Clobbit playing against MCTS. As you can see, when playing as the first player, the Clobbit has a nearly 90% win ratio over 5,000 games. However, when we let Monte Carlo play first, it gets the overwhelming win majority. As a result, it's pretty clear that the first player in any Clobber game has the advantage. Some fundamental elements of Clobber made it difficult to know who is winning at any given time. Each player will lose one piece each turn, so you can't simply have more pieces than your opponent. No piece is inherently any more valuable than any others, and the number of moves available to either player is by definition the same for the other player. How then to determine the value of any given board? In the time we had, we were unable to come up with perfect answers to these questions, but what we did determine will hopefully provide a basis for further study. The strategic elements that we were able to describe algorithmically are blocks, orphans, and stranded pieces. A block is any group of pieces bound by the edge of the board or empty spaces. An orphan is a piece that currently has 0 moves, but is in a place where it might get more later. A stranded piece is one which is in a block, could just be itself, with no opponent pieces at all. Fundamentally, the Clobbit is a 3-tiered strategy. The first 2 take the form of greedy search heuristics. The final strategy is alpha-beta pruning. Why not just run an alpha-beta pruning strategy from the beginning? Chiefly, we have not yet developed a way to assign a numeric value to any given state, meaning alpha-beta has to run to every leaf in order to return values. On even a moderate-sized board, computation time became an issue. The first tier is called min-op moves, or minimum opponent moves, which simply tries to reduce the moves that either player can make. Obviously, this could never be an endgame strategy, but it's one of the quickest ways we've found to rapidly shrink the scope of the board without giving up any early advantage. Called the second tier max flex, short for maximize flexibility. This checked each possible state and assigned them all of value, taking its own non-orphan pieces and subtracting the opponents. While this does not specifically seek to strand pieces, it finds that it does so over time. With the scope drastically reduced, alpha-beta pruning now provides a robust endgame strategy in reasonable computation time. The final decision was when to iterate changes in strategy. The simplest option was based on the number of turns taken in the game. While the theoretical maximum number of turns possible on a 5x6 board is 29, our tests of random versus random showed early average times tended to be 16 to 20 moves long. Thus, we determined to run min-op moves for the first 5 turns, then max flex to 10, and finally alpha-beta pruning for the endgame. Potential research into the applications of AI in Clobber are far from over. There's a particular enhancement to max flex we would like to add, which we call max strand. Basically, it would search states at n depth and seek out scenarios which would strand many of the opponent's pieces. Other plans for further study include applying machine learning to adjust the triggers which switch strategies. A Bayesian model could be set to run countless minor modifications to such variables as number of moves remaining, or the number of stranded pieces, and learn the optimal situation to use any of the given strategies to reduce computation time while maintaining an acceptable win ratio. The final area we think bears further research is a means of assigning a numeric value to any given state based on its advantage to one opponent over the other. This could potentially make alpha-beta pruning a viable option when run at limited depth. In conclusion, our research revealed some very interesting food for thought. We were able to prove that the first player has a steep advantage in this game. Despite this, the Clobbit provided a more robust strategy than a standard MCTS in comparable computation time. We have outlined a number of distinct and discrete possible improvements for further study, and a small number of more abstract things to consider as research continues into applying AI technologies to this expression of game theory.